Alright guys, welcome back to my channel. Today we're going to be talking about orbitals. In the next video that follows, we're going to be discussing hybridization and steric number. So stick around if you need some help figuring out the grand topic of orbitals. Alright, so first of all, what is an orbital? So an orbital is actually a mathematically derived volume space where an electron is most likely to be. So we really can't determine where an electron will be at a specific point in time. There's no way for us to know. However, we can determine the spaces where it's most likely to be through probability and statistics. So some mathematicians and some really smart people figured out these functions that when you graph them gave you 3D volumes of spaces where electrons are most likely to be found hanging out. So we're going to be talking now about the types of orbitals. I want to prelude this by saying that these that I have pictured are definitely not all of the orbitals that are out there. There are an infinite number of orbitals since there technically is an infinite number of energy levels, but the ones I have here are those that you're most likely to see in your kind of entry-level chemistry classes for middle, high school, and college. This is about all you're ever going to need unless you plan on taking some super advanced chemistry classes such as in the upperclassmen graduate level. So let's start out with our 1 and 2s orbitals. Now, anytime you see the letter S, it stands for sphere. So whenever we want to actually draw the 1 and 2s orbitals, they're just going to look like spheres. Now remember, we're working on the zxy plane, meaning we're working in 3 dimensions. Oops, that looks more like an oval. Let's try that again. Now, the one thing you want to notice is that the 1s is significantly smaller than the 2s. This is important. So we know that as we go down the periodic table, the atomic size increases because the energy shells increase. Therefore, the s orbitals are also going to be increasing as we go down the periodic table. It's also important to note, as you see down here at the bottom, that the number in front of the orbital letter signifies which energy level it's located in, and also that the lower the number, the lower the energy, and the more stable the position. Therefore, the 1s orbital will be lower in energy and more stable than the 2s. Alright, so now let's move on to the 2p's. Now, the first time we ever see p orbitals is in the second energy level. This also means that for any higher energy levels, such as 3, 4, 5, and so on, you will always have 3p orbitals as well. They may not necessarily be filled, but they will be present. There are no p orbitals in the first energy level. This is important. Another thing to note is that these p orbitals are named based on one of the axes in our graph. So we have 2px, 2py, 2pz. The letter associated with the orbital indicates which axis we will draw the orbitals along. So the first one is the 2px. So we're going to draw it. The axis, these are dumbbell or kind of teardrop shaped. Now you'll notice that I didn't connect them in the center part. I kind of left this space open, and that was intentional because there really is no space. Well, there really is nothing here. So these two kind of volumes of space are not connected in the center. And this is something really important and actually a really cool phenomenon. Scientists have been yet to explain this, but if there's electrons in one side of the orbital, they are actually able to jump into the other side. They're literally able to almost teleport themselves from one end of the orbital to the other because, again, they don't pass through the center part. So this is a really cool phenomenon. Nobody really understands how it happens, but if you definitely want to win a Nobel Prize, go ahead and see if you can figure this one out. Okay, next we have 2py. So we're going to do the same thing, but we're going to draw this on the y-axis. Oops, sorry, I'm not the best drawer. And finally, we have 2pz, same thing, but on the z-axis. Alright, so now that we're finished with the p orbitals, we're on to the d orbitals. There are 5 d orbitals in total, and the first time we see them are in the third energy shell. Now, it should be noted that along with the d orbitals in the third energy level, there's also, remember, a 3s and 3p orbitals. So 3px, 3py, and 3pz. And if you remember our rules for the atomic orbital filling model, those are always going to be filled before the d orbitals. But I've only included the d orbitals here just to keep it a little bit more simplified. So, a little bit different from the p orbitals because they're going to have 4 spaces, but similar to the p's, they're all going to be separated. And then each of these letters, so the first one, 3dyz, indicates which axes we're going to draw the volumes in between. So unlike the p orbitals where we drew them along the axes, we're going to draw these orbitals in between. So the first one is yz, so it's going to be in between the y and the z. So we have 1, 2, 3, 4. Perfect. And I understand that these are definitely going to be harder to see in your head in 3D. So if you want, go ahead and search a picture of these guys up online because the computer generated pictures are definitely better than what I can draw. So next, we have the 3D XZ, so it's going to be between the X and the Z. And 4, now XY, so between X and Y. And another thing I want to note is that it doesn't matter how you draw your X, Y, Z axis, you can have the letters pointing in different directions, just so long as you have all 3 of them. Okay, now we're to x squared minus y squared. This one's a little bit different because we're actually going to draw the orbitals on each of the x and y axes, just like we did with our p orbitals. So we have 1, 2, 3, 4. And finally, we have z squared. This guy is definitely my favorite just because he's the most interesting looking out of them all. My high school chemistry teacher told me this one was a ballerina. I think it looks more like a person in an inner tube, but call it what you want. So we're going to start by doing 2 nodes on the z-axis. And then we're going to draw our little tutu or inner tube or donut. Perfect. This guy's definitely my favorite just because he's the most interesting looking. Alright, now that we have all of our orbitals drawn that we want, we're going to move on to the periodic table and how to use it. I do want to note, however, that after the d orbitals, you may see something called the f orbitals. I don't have them listed here because, again, you're not ever going to need to know these in these types of classes, like in high school or entry-level college. But if you do take high-level courses, you may need to know those. But for right now, we're just going to leave them be. But they're definitely interesting to look at, so go ahead and look at some pictures of them if you'd like. Okay, next, using the periodic table. So you may be wondering, how in the world are we going to be able to get any information just by looking at the periodic table? Actually, the periodic table is a great visual tool when you're in the middle of a test, you're super stressed out, and you don't have time to think about it in your head. But there's about 3 rules I want you to keep in mind. Instead of thinking of these numbers as the period, think of these as the energy levels. So when I'm talking about the energy levels, I'm talking about these guys. So we have our energy levels 1 through 7. Remember that these are associated with different atomic sizes as well. But for now, we're going to think about them as energy levels. Next thing I want you to remember is that each orbital can hold at most 2 electrons ever, please, please never ever draw an electron or draw an orbital with more than 2 electrons, please. There are a few exceptions such as selenium and silicon and xenon, but we're really not going to worry about those guys. 95% of the time, only ever 2 electrons. Please don't forget that. Then next, think of each box on the periodic table, so each box for each element is equal to 1 electron. And this is going to help us really visualize these orbitals. So first, we need to remember that we have our s orbitals, right? And they're only ever going to hold 2 electrons. Well, where can we find these s orbitals on the periodic table? We're going to find them in the first 2 columns. Now we do have a space missing right up here. This is really going to be helium. That guy just kind of got scooted over to the right for a good reason, but just remember helium is also a part of these first 2 columns. Next, we need to figure out where our p orbitals are going to be. Can you guys figure it out? It's going to need 6 boxes next to one another. Yep, right over here, where most of our non-metals are going to be. 1, 2, 3, 4, 5, 6 columns. And then finally, we need our d orbitals. This should be pretty easy to spot. It's going to be 10 boxes next to one another. Right here in the middle with our transitionary metals, right? 5, 6, 7, 8, 9, 10. Nice. Now, the last thing you need to remember is that each 2 columns represents 1 orbital. So the 2 columns here represent 1 s orbital. Remember, the number is determined by the energy level. 2 columns over here represent 1 p, and 2 columns over here represent 1 d. Remember, in total, for each energy level, we have 1 s, 3 p's, and 5 d's. Alright, beautiful. And now the last thing I want you guys to note is that we fill left to right. So you are going to need to remember some of those rules you learned for your atomic filling space model. So remember the Alpha-Val principle, the Pauli exclusion principle, Hund's rule. It's the idea that we fill the lowest, we have opposite spins, and that we fill in one direction first. So I'm going to give a super quick example. We have our 1s, 2s, 2p. So we know that our 1s is going to be lowest in energy, so we fill that one up first. Remember that there are opposite spins, so we draw them up and down. Next we go to the next highest. And then finally the last rule is that we draw them in the same direction first. We're going to go up, 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 and then we're going to go back down and do down, down, down. Do not do this. Do not do that. We have to draw them in the same direction first. Alright, the next thing I want to know. I said fill left to right, but you'll notice something here. Something wrong with the D's, right? Well, in our last example, we know that there's 3 D's, but there's only 4 rows, right? We only have 1, 2, 3, 4 rows. So where's the 3D? Well, so the 3D is actually this row right here. Then we're going to go down to our 4D, 5D, 6D, and so on. So really, we have our third energy level. It's going to go like this. It's going to go down, and then it's going to back up. And that's our complete row. But don't think about it like this. The way the periodic table is now, is actually how you will fill it up in order. So like we said before, that we always fill the lowest orbital first. So we would go, let's go to 3s, 3p. Now we're going to write the next orbital that will be filled. And instead of writing 3d, we're actually going to write 4s. Now I know that may seem weird, but the 4s orbital is actually lower in energy than any of the 3D orbitals. Therefore, it'll get filled first. Then write 3D. And then we're going to write 4p. So actually, it kind of works out because how we fill it still continues left to right. But just so you guys can see, we're going to go up, down, up, 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 down, 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 up, down, up, and so on and so forth. So you see that we always fill 3D last, after the 4D. Okay, let's choose an example and see if we can figure it out. Let's choose fluorine. Fluorine seems like a good choice. Now remember that we want to mainly look at its valence electrons. Now if you don't already know how to draw a Lewis dot structure or an orbital structure, I would definitely go and review that before moving on. So you should also know what valence electrons are. They're going to be our outermost electrons in our shell. So let's go ahead and draw the structure for fluorine. So we first have 2 electrons, then we have our next ring, and we're going to have 8, right? Yeah. Nope, sorry, we're going to have 7, I forgot. We're doing fluorine, not chlorine. 1, 2, 3, 4, 5, 6, 7, 8. Perfect. And we, oh gosh, I just said that. Sorry, 7. So we know it's going to have 7 because if we count across, we have 1, 2, 3, 4, 5, 6, 7. Okay. So these last few electrons are going to be what tells us which orbitals are filled. Okay, so we can see that fluorine is in the 2nd energy level, so we're going to need at least the 1s and the 2s. Then we can see fluorine is in this green column, so it's going to be, it's going to have some of its 2p orbitals filled as well. So we're going to go ahead and draw our model. Remember, there's 3p orbitals in every energy level. So now we're going to fill up. Remember that the 1s are going to be these 2 electrons on the inside right here. These 2 electrons represent the 1s orbital. So we're going to go ahead and fill those up. Then remember the electrons in the 2s and 2p are represented by our valence electrons. So these 7 ones in the outer ring. Okay, so we're going to go ahead and fill those guys up. So we know we have 1, we have 1, 2, 3, 4, 5, 6, 7. So we see that we only filled up 2 full p orbitals. We did not fill up the last p orbital, and that's important because the amount of electrons that we have and in which orbitals they are determine the properties. So all of these elements that are in the same column have similar properties because every single one of them has only 2 of their outer p orbitals filled. And that's something important to note because this allows for certain types of bonding and reactions to occur. Alright, that's it for our orbitals. In the next video, we'll get to hybridization. If you have any questions, please put them in the comments and I'll try to get down to them. I hope to see you again next time, guys. Bye.